insulin secretion in pancreatic islets via multiple dynamic modes.
I want to thank Sinha for the invitation and all the organizers for I've been having a great time here. I want to start with a little bit of a disclaimer, and I'm not really going to talk about neuroscience per se. It's more endocrinology than anything else. Although there are interesting interlacing effects relative to neuroscience, and you may find these things interesting as I describe them. So what I'm going to talk about is glucose-stimulated insulin secretion, and we'll see in a minute why that is interesting to us, and what does that have to do with having a neuroscience like audience in front of me. What am I doing here? So, right at the outset, let me describe the pancreatic insulin system just as a refresher for most of you. This here is the pancreas. It's an organ that sits in the abdominal cavity, and the pancreas is, of course, the site where insulin is packaged and delivered into the blood in response to a glucose stimulus day after having a meal like we just had. So very likely glucose is very high in our bodies, and so is insulin is picking up as well. So what we'd like to understand is why, or how, rather, what are the biological mechanisms by which glucose stimulates insulin secretion. Insulin is, of course, necessary for the glucose to be taken up by peripheral tissues such as muscle and adipose and all of the other tissues that require glucose, which is all of them. It's only the presence of insulin that the glucose is taken up by these tissues. And of course, this also has to do with one of our long-standing interests, which is to do with diabetes. Why is there rising incidence of diabetes in the world? Diabetes traditionally is defined by insulin resistance, which then leads to hyperglycemia, chronic hyperglycemia, which then has secondary complications and so on. And this is a problem for Southeast Asia especially, India and China in particular. And I won't get into diabetes because we don't understand enough of it, but I'll try and understand the basic, I'll try and describe to you what we understand about the basic physiology of how glucose stimulates insulin. So you would have thought insulin, glucose-stimulating insulin is a very simple biochemical mechanism. Glucose gets transported into the cell, and that causes insulin to be secreted. What could be harder than that? It turns out that for several decades we've known that there is actually an electrical signal that accompanies it. There's this very nice bursting pattern that is associated with the islets of Langerhans. The islets of Langerhans comprise about 1% of the entire pancreatic tissue, and this is the endocrine tissue of the pancreas, and this is the only site in the body, at least the predominant site in the body, where insulin is actually packaged into this little vesicle, and then exocytosis takes place directly into the blood. So in the islet of Langerhans, there is a wonderful bursting pattern that is associated with it, with insulin secretion, and this tissue here is dominated by gap junctions. There are no synaptic couplings in this, although this tissue is capable of being excited by cholinergic input. There are no evident synaptic kind of structures that are there present in the line of Langerhans. I'll talk a little bit more about the geometry and the connectivity, if that's going to be important for the theory that we're building. So what does a bursting pattern like this have to do with secretion of insulin? This is what we like to understand. Notice a very interesting trait of this. This is on the order of several minutes. It is a hormonal rhythm, in a sense. This is on the order of burst interval is on the order of about 5 minutes. So this is very, very, very slow compared to neuron's time scales. So the interesting question that's going to arise for us is, what are ion channels doing there? And in fact, we sort of understand what the ion channels are doing there, but how is such a slow rhythm brought about in the context of ion channels, which are accompanied with relatively fast ion channels, neurons and such. So this is what we like to understand, this kind of behavior. How is it a slow time scale is arising in this scenario? So a little bit about the pancreatic tissue itself. As I said, the endocrine tissue is about 1%, so it's a very small fraction, nonetheless a very important fraction. It only requires a little bit of insulin to actually stimulate glucose uptake in all of these cells. Glucose rises in millimolar quantities and insulin rises in picomolar quantities. So, it's a gating signal more than anything else. If you look at the islet close up, this is a canonical diagram of a mouse islet. You see a core of beta cells, about say 1,000 beta cells on the order of between 1,000 and 5,000 beta cells, and surrounded by a layer of mantle of alpha cells. Alpha cells secrete glucagon, if you recall from basic biology, and then there's also delta cells in there and so on. And we're only starting to understand how alpha cells and beta cells are in contact and how they interact with each other in terms of glucose homeostasis and the rest of the body. But what I'm going to talk about largely here is the beta cell physics. I might add as a caveat that this is a canonical textbook picture of an islet. So this is a rat or a mouse islet. Human islets are actually quite different from this. In human islets, alpha cells tend to be in larger proportions relative to beta cells. So approximately a 50-50 balance. And we don't know what that is really. This is one of the interesting questions that I won't get into now, but it's something that we study. We're starting to study that. So my job for the first part of this is going to be to describe how glucose interacts with these ion channels on the membrane, and how we might build a theory, a mathematical theory for not only the pancreatic bursting system, but also what does glucose do to the cell. So, the consensus model of glucose-stimulated insulin secretion, this is consensus by virtue of the fact that ion channel behavior is known in these cells for the longest time, say for over 2 decades, was discovered in the early 70s, or maybe even earlier than that. The general argument is that there are calcium channels and potassium channels that are sitting on the membrane. Calcium, there is a kind of potassium channel from the ATP sensitive potassium channel that is sensitive to changes in ATP, to despedation in the cell. So when glucose goes up, presumably that causes ATP to be phosphorylated with ATP in the mitochondria, and that is sensed by this KATP channel, which then closes, allowing for depolarization via the L-type calcium channels to bring the cell up, bring the cell depolarized, get the cell depolarized, and that brings in calcium into the cell, and this whole thing cycles because it mentioned at some point or the other calcium will leave the cell, and it's this pulse of calcium that is synchronized with insulin secretion. So when calcium rises, insulin is secreted. So we want to understand. So this much is accepted in the literature. There's a lot of evidence for this to be true. What is not known is what are the metabolic components. How might they interface with these ionic components at all? So what's the evidence that there might be metabolic components at all at play here? Well, let's take a look at some of the bursting patterns that have been recorded in beta cells. These are electrophysiological traces from islets, and you can see from the labs of Les Satin at the University of Michigan. This is a very slow oscillation of the order of 5 minutes interval, as I showed you in the trace earlier. This is calcium recording, but there's also a high frequency oscillation that is sometimes observed. This is several cycles in a 5-minute period, so this is on the order of a minute or so. And then there are these funky oscillations which are sort of, it's almost as if the cell is trying to go into a bursting mode and it can't make up its mind whether it wants to spike around or whether it wants to burst. So these are what we call accordion-like bursting. These are mixed mode oscillations. So what's the genesis of all of these different types or formats of bursting? Can we explain why all of these can be seen in islets, in isolated islets? So the ideas that I've been developing in the field for, say, the last 10 years or so, is to look at an evolutionary viewpoint, and that is to say, well, we know that ion channels are known to be important to these cells, and both ion channels are in ancient behavior, and so is metabolism. So now glucose in the beta cell is not only a molecule for respiration like it is for any other cell, but it is also a molecule, it is also a signaling molecule. So could it be that the beta cell has integrated metabolism and adjoint behavior at some early point in evolution, and that these two features, and that these two processes are entangled in the beta cell because glucose has this dual personality in these cells. So that's what we'd like to ask. So what's some of the data that supports this kind of an argument, or that provokes this kind of an argument? Well, here's some oscillations recorded from Paul Kennedy's lab in Kennett, Michigan, I think. This is calcium. You can see three different kinds of patterns. One is a fast oscillation, one is a very slow oscillation, and then there's these mixed mode oscillations mixed sort of oscillations that I spoke of. You can see that oxygen and zinc is oxygen oscillates in these cells, and then zinc is a surrogate for insulin because the C-peptide chain is wrapped around a zinc ion, which is then packed into a vesicle, into an insulin vesicle. So zinc is seen to oscillate in tandem with the calcium, but then there is oxygen that's oscillating, and one asks the question, well, why could oxygen be oscillating? And the answer that comes across the end is that, well, metabolism is oscillating in these cells. So somehow the electronic components that are oscillating are driving a metabolic oscillation. Well, is that fair to say that? That's the question we'd like to ask. So we need to build a model that will allow for not only electronic components, the electrical components of the cell membrane to oscillate, but also which will have some involvement of metabolism in the sense of oscillations. I think I've already said this. So here's one way to go about it, and this is setting up the stage for a model that is being written down by Richard Bertram at Florida State, R.D. Sherman at NIH, and their collaborator Les Satin at the University of Michigan. So I'm going to describe that model to you in a little bit. I'm setting it up now. Well, here's the idea. We know that glycolysis is one of the processes that are known to oscillate in cells, and it has the right time scale. It has a 5-minute, 10-minute, or a 15-minute time scale to oscillate on these slow time scales. So the question we'd like to ask is, might we expect glycolysis to oscillate in these cells? And if it is, then how does it interact with the electrical components? So here's a possibility. Let's say glycolysis is active. How might that interface with the electrical business? That's easy. That's because the PCA cycle will change ATP-ADP ratio, and the potassium sensor will pick it up. The potassium ion channel, KD sensor, potassium ion channel will pick it up. So there is a feed forward from glycolysis onto electrical. Let's ask if there is a feedback from the electrical system onto glycolysis. There are models that have been written down, very intense, very difficult models, very elaborate models that have been written down by Magnus and Kaiser that have implicated a rise in cytosolic calcium to change mitochondrial action, which then might feed back onto glycolysis. So there are models that have been written down. We know that that is a plausible scenario. So the next bit is to put them together in a mathematical model. And this was done a couple of years ago, in 2004, by this group that I spoke to you all, and they call this the dual oscillator model. So the dual oscillator model is going to take this scenario, and what they decided to do was they take one of the electrical/calcium. So electrical calcium models have been around for since the 80s at least. So there is some electrical model in the works of Kaiser, Che and Kaiser. They were one of the earliest proponents of these electrical models. They came up with some first. And then they also took a model of glycolysis, in particular one that is known to oscillate from pulse mode that was written in the early 1990s. And then they simplified some of the equations of the Magnus-Kaiser type that involved ATP, and some intermediates of that process, A and B, and they coupled it all together. So the glycolysis is going to act on the mitochondrial variables, which is then going to also act, which is also going to have the feedback on the electrical components. So that's all of these connections, both directional, the bidirectional feedback that goes from the glycolysis onto the electrical. That's going to be all incorporated in one giant problem. So those are the equations, and I'm not going to walk through all of this, it's pretty intense, except to point out that here's the usual Hoskin-Huxley framework for writing down the voltage memory with voltage potential. There's a potassium channel, a calcium channel, a calcium-dependent potassium channel, and 8 ATP channel. So that's just to show you the makeup of the ion channels in these cells. And then there are these equations for the usual kinds of cytosolic calcium dynamics and ER calcium dynamics with buffers stuck in there, and all the pumps that the I is in the anti-calcium channel pump, and the KPMCA is the plasma membrane calcium pump. So that's this much is a voltage calcium model, and then there is glycolysis itself. So in this model, this is Paul Smolin's bit. In the Smolin model, the variables that he keeps track of are G6P and FPP, fructose 6-phosphate and glucose 6-phosphate. Those are two variables. I'm sorry, FPP, fructose 1,6-bisphosphate. And these have feedbacks onto the AMP system, sorry, the ADP system feeds onto this via this equation. This equation was written down by Richard Bertram on the basis of reductions following the kinetic isomatrix kind of dynamics. So, so those are the equations used. And here's what the model is capable of achieving. The model, if you tweak around, play around with parameters in the model, and there's not that many parameters that we need to control. There's KCA, G, KCA, and GCA, and a bunch of other variables that you need to control, about 5 or 6 different parameters. And this model is able to produce all of the oscillations that are relevantly seen in experiments. So here, for example, is a fast oscillation. This is in minutes. This is a slow oscillation on the order of 5 minutes. This is faster than that. Here's something called a compound bursting. This is bursts of bursts. There's a group of bursts that fire rate happening, and then there's a large cohesive here, and then the group of bursts that fires again. This is something the lab calls compound bursting. Here's an accordion kind of bursting. The bursts never have very large quiescent here. It is largely active in terms of bursts, but they go in and out in terms of the frequencies of these bursts. This is something very interesting called sub-threshold bursting, but this looks as if it's not even doing anything, but there's a small ripple of memory potential. How does it matter? Well, for the longest time, people did not see slow bursting, presumably because they were not looking in traces long enough to pick up slow bursting. This is a very good indicator, as the theory will point out, of metabolism oscillating in these cells. So my argument is going to be electrical activity is able to oscillate on its own. This is known from various and sundry sources, that glycolysis oscillation is going to interface with electrical activity to produce all of these different patterns. And I'm going to show you a subset of these, in particular the slow bursting pattern, as being relevant in how we understand that. Okay, so we wrote a paper a couple of years ago that we tried to understand then how is the electrical component, how is the electrical bursting interface with the metabolic bursting. So I'll show you a little bit of that. So for those of you who follow classical bursting models in the work of, for example, Eugene Izagevich and others, the models that have been written for bursting in pancreatic cells have what is known as a square wave burster or a fold chromoclinic type. What that essentially means is that there are two states the system is able to be in. One is a state of equilibrium and the other is a state of periodics. And these two are, the system is bistable, so they're existing at the same parameter value. And another slow variable in the early models was calcium, drives you between these two systems, between these two states alternately. So there's a hysteresis loop in there. Calcium changing in the one direction will take you along to the fold point, and then the system has no alternative but to go up into an oscillatory state, which is then traversed in the opposite direction and falls off a homoclinic back into a cycle state and so on. And this process is how mathematicians understand bursting in these cells. This is a model of just the electrical components. So this is 3 or 4 equations at best. Voltage, one of the gating variables, say calcium cytosolic, and if you push the analogy too far, maybe you can build in calcium ER as well, although that has an interesting set of dynamics and a completely different set of phenomena arise over there, which Richard has clarified in great detail. I won't talk about that. For me, ER calcium and cytosolic calcium are going to be taken on an even key. Okay, so those are the equations again, just to get an overview of things. And I draw these arrows to point out that this is ADP, G6P, FBP system. In general, we're going to expect this to be a slow system because it involves on slow time scales. We're going to expect this system to be able to have fast dynamics and what the bidirectionality in this is for calcium through the Magnus-Kaiser effect feeds onto the ADP equations into the mitochondria, and ADP of course is a sense of ADP is a molecule that is sensed by KDP. Actually, the ADP is sensed by the KDP channel. So these two systems are going to interact with each other. Let me split them up and show you individual components of what the electrical activity is doing in this model. The electrical activity has this relatively clean. This is similar to the photochromoclinic scenario that I showed you. In fact, it's exactly identical except for a couple of nuances. So here, these are states, even though I don't show them with oscillations riding on top of them. This is the state of oscillations. This is a state of equilibria, and presumably one is going to be able to travel back and forth between these two, complete the hysteresis, and get reversing back. If anyone wants to discuss it, there's a lot more to it than that. But let's just go with this much for now. This here is the glycolytic system. Oh, I forgot to say that I'm making it stationary in this. So the way to break the two systems is to assume that the glycolysis is not doing anything dramatic in terms of having the dynamics. It will make it basically a parameter, and then watch what happens to the electrical subsystem. In this, I'm going to take the loop going the other way, the feedback going the other way. I'm going to freeze calcium, because calcium it becomes a parameter for the ADP, FBP, G6P equations. So this is the state of glycolysis. And this is influenced by the amount of glucokinase rate that is there. So that is to say, glucose will affect this. If you look closely, this black line over here, at low glucose rates, that's the equilibrium configuration that glycolysis likes to be. If you raise glucose just a little bit, in this case RGK is made to go to 0.2 from 0.02, and then you see a pair of red lines. Now those are the limits of the oscillation at an intermediate glucose level. At an even higher glucose level, again, the system switches back via supercritical hot bifurcation into another stationary state. So stationary in between glucose allows you to oscillate, and then stationary again at high glucose. So, and now we put these two things together. So here's how the two diagrams overlap, and this shows us how the cell is able to oscillate at this low frequency. At the system, let's take this branch, the active branch. So the active branch is actually determined by the electrical subsystem. So the electrical system pins the entire system. This is the total system here. It pins the entire system into this manifold of periodics, and in the smaller model, or in the smaller plus mitochondrial model, the metabolic dynamics is such that when the calcium is high, the system is driven through a high ATP state, a low ATP state. So it reverses the direction in which the direction in which glucose is taken. So when you are in a high calcium state, you're driven to the right, you fall off the knee, and then the calcium is low, and when the calcium is low, that promotes an ATP to ATP conversion that reduces the ATP levels in the system, and then you move backwards, and then we jump again at the fold point, and you keep reversing this loop again. So the electrical system sets a skeleton for the excited state and for the stationary state of the oscillation, and it is the slow glycolysis that drives it back and forth. So the hysteresis is completed by the slow glycolysis. And then, so then one can imagine that the oscillation takes place on the slow time scale. Okay, so this is how we understand bursting in pancreatic cells. There's much more that we know about this. let me give you a quick gist of it without deciphering for you all of the different patterns and how we understand those. So I showed you this particular case out here. I'm sorry, the case of slow calcium. But then in low glucose conditions, the cell can be either stationary or it can have a low threshold oscillation, or it can even show a fast oscillation. These are all experiments that have been conducted and have shown the different things can happen in low glucose. In a high glucose scenario, you typically get a slow oscillation, as in this case or in that case, or you may actually get a very high, a fast frequency riding on a high threshold. So we, using the theory that I just showed you, are able to decompose all of these different behaviors in terms of the basic framework. So if anyone's interested in following it, the reference that I pointed out earlier would be the place to look, and we can certainly discuss it. So we understand glucose sensing in the islet, is my view. So far, I'd like to change tracks a little bit. So far what we've done is, we're sort of looking at a stylized islet, in the sense that synchronization in these islets amongst the beta cells is sort of taken to be a canonical reality. So we are assuming that all of the beta cells in the islet are sort of doing the same thing, and whatever this unit is what we're representing the behavior for. We're calling it a beta cell, or we could call it an islet, but it's this conglomerate of things. If you want to understand spatial differences or spatial effects in islets, then we have to modify the formalism. We actually have to construct networks of beta cells and ask how these cells interact. They can produce either synchrony or not. So that's the other aspect of things that we're interested in, and we've been working on this for a little while. We use homogenization theory in order to build tissue scale models, tissue being the islet and cells being the beta cells. In fact, there is a third subcellular scale that I'm not going to talk about, which involves ER calcium interacting with cytosolic calcium. So this is work done with at different times with Avery Friedman, Martha Sherman, and James Sneed. And I'm going to try and tell you a little bit about what we want to do when we do homogenization. So homogenization is going. It's traditional in the cardiac field where you have tissues that are excitable tissues that are electrically coupled. So homogenization theories have been around since the 90s in the form of cardiac bidomain models, where the New and Kasalska, I think, is the first reference where they've derived the bidomain equations for cardiac tissue in terms of a homogenization argument. And we are interested in a homogenization argument, apart from traditional reasons, is because we'd like to understand how is it that this packing of the spheres, these are the individual islets here, these are individual beta cells here, what is the influence of this geometry on the conductivity properties, the effective conductivity and the effective permeability of different species, of the conductivity of the electrical phenomena and permeability of calcium and other species that are passing across between these in these cells. So the general framework of homogenization theories is to consider large spheres. Beta cells are very close to spheres, so we consider spheres. And gap junctions are holes in the syncytium. So this is known as the syncytial model. This was developed for biology, as I said, for the cardiac models first. And we did it for islets because it hadn't been done for islets, and we'd like to know the answer for islets, and not for cardiac tissue, which is a different kind of tissue. So we did that. So the argument here is kind of going backwards from, it's like taking, it's the opposite of compartmental modeling. So in the neuroscience literature, the work of Will Gall and others in the Cable equations for a very long time has shown how to do compartmental modeling in an effective way. That kind of technology does not exist, or did not exist in the beta cell literature, so we had to reconstruct it from the beginning. So we switched to PDE models first, and then that gives us an insight by how to discretize the PDE into what are known as lattice differential equations or network, OD network models, the compartmental style models that can be used for these cells. So this is a lot of math, but all of it is just to say that we write down equations, reaction diffusion type of equations that are valid in the actual microscopic space. You use a method called multiple scales. You expand along a large time scale valid at the scale of the islet, and another variable is time, and the other variable is the microscopic magnitude order of magnitude, and you expand, and then you do matching of different powers, and at the end of it you get an equation for the coarsest order of the variables that you're interested in. Here's the voltage equation, goes to the calcium equation, valid is the zeroth order. These are the zeroth order equations, and they are valid at the scale of the item. So all I want to show here is that this is a reaction diffusion kind of equation, and what we're really interested in calculating on the basis of the microscopic geometry is what these numbers are. Is effective diffusion coefficients or effective conductivity coefficients. So in order to solve for the effective conductivity or diffusion coefficients, you have to solve an auxiliary problem called the cell problem. Again, this is a whole bunch of mathematics. If anyone's interested, we can discuss this. Here's a simulation that says well, the cell problem is composed of a vector field composed of 3 scalar fields. So this is a computation of the 3 scalar fields that are involved in that computation. And what you get from computing all of this is that the effective diffusion coefficient relative to free diffusion coefficient is about half. That is to say, constrained by this geometry of having to travel through these different spheres, through these little holes in the synchrotron, diffusion is effectively slowed by a factor of 2. And so is conductivity. That's all it says. And it takes a bit of work to get there, but that's the order of magnitude in this model for the effective diffusion coefficient. Okay, so that's all good and well, and this is just mirroring the calcium bidomain homogenization ideas. But that's a little bit bothersome because synchrotron models assume that gap junctions are holes, but as we've seen in several talks, including Vatsal's, that the gap junctions are a lot more intricate structures, and there are a lot more nuanced. There are all these connection molecules. So there's this plaque which allows for several pores that allow things to pass through species, pass and so on. So how do we if we wanted to build in this structure, how do we go about it? And I think the reason we need to build this structure in is because assuming a big hole leads to problems. So I want to try and convince you that part of that argument, that we can do better than simply assuming synchrotron models. So, recently I've been working with James Sneed to come up with something called the dough ball model. And the dough ball model, each cell is sort of a unit, and it is separated from the next by gap junction plaques. So these spacers, these blue spacers that you see between cells, is a gap junction plaque. To remind you, the synchrotron model would just simply assume a hole between these two and things are just getting across. We assume a particular structure for these and ask, oh, how do the equations change? If you put in something, what we have to address is what are the constitutive equations for what goes on at the plaque itself. At the plaque itself, what we do is we assume an interaction of the form So the flux that is going across, instead of having a simple continuity type of relationship, is directed by what's the voltage here and what's the voltage there, and the difference drives the flow. So in that sense, it's different from the usual synchrotron model. We insert a parameter called G. G stands for the relative strength of this flux, and I'll say a little bit more about G, what that does. So we write these down, proceed with the homogenization. Again, you get reaction diffusion equations of a very similar type. What's different is that you actually have to solve a cell problem for this dough-ball coupling in a slightly different manner, in a completely different manner in fact. But now you have to solve a cell problem that involves two cells sitting in this periodic unit, and you have to have the rule for how the flux changes, the rule given by this equation, essentially. Okay? So we go through this, and as a snapshot here is the computation. So there are two cells in this periodic unit cell, and they're interacting through this dough ball style of coupling that I described here. One solves the cell problem for this, and what's the answer now for what the effective diffusion coefficient is? Well, we have a parameter in there called G, which is the relative strength of the plaque coupling relative to cytosolic coupling. So I'm going to take G and plot it on the x-axis. That's my parameter, and we're going to plot the homogeneous diffusion coefficient as a function of G. So here's how you get the sigmoidal curve, which is very well fit by this equation here. And here's how we read this. So at very large G gap, G gap is again a sort of a parameter, a dimensionless parameter that stands for the dielectric gap junction plaque versus the cytosolic gap junction convergence. Right? So at very large G gap, you asymptote towards the syncretion model state. So essentially you come close to 0.5 in terms of the effective diffusion coefficient. As you go away from being the syncretion model, that state, as you tune up, you go in this direction, as you tune up the dielectricness of the gap junctional plaque, you go away from being purely sinusoidal, you have to pass through, you make it denser and denser, you make it harder and harder for the conductivity to pass through, and for the permeability to be, and the permeability becomes lower, and then you start moving towards zero. So G gap gives you a tunable parameter that stands for how much of the gap junctional plaque is being lipid versus how much of it is pores, connection pores that allow for direct discharge. So we have this parameterization of the effective diffusion coefficient. Let's see how we might use it. So what's the point of going through all of this? Let's take a small case study. One of the questions that is endured in pancreatic modeling in the field of modeling pancreatic tissues is to ask how strong are gap junctions. There are estimates in the literature available, of course, and there are problems with every sort of experiment that you can do. You can do a paired recording with two sharp electrodes, and then you are excising away two cells from the entire tissue, and so on and so forth. So all of them have been criticized. Modelers have tried to assess this problem by doing a modeling study. So a couple of years ago, the lab of David Briston did this very wonderful experiment in a microfluidic chamber. Here is a microfluidic plate. They place an islet in this actuator, they press it between these two, and they allow for different concentrations of glucose to be flowing on the two sides of the islet. So this side of the islet is high glucose, and this side of the islet is low glucose, and what they're expecting to ask is, if this side of the islet is oscillating, if it's stimulated, do the gap junctions carry that oscillation all the way across the site that is not stimulated on its own? If the waves travel all the way across, then gap junctions are doing their job, they're synchronizing the islet, and so on. If the waves do not travel across, then the gap junctions must be weak. So the answer that they found was that waves do not travel across. The site that is excited shows oscillations, but there is a level beyond which this wave does not penetrate all the way to the islet. So we wanted to ask if we could reproduce this sort of experiment in a modeling setup. So we used a dough ball model to see if we can do this. Okay. This is still an open problem, and I'll actually tell you why. We don't know how to do this with the dual oscillator model dynamics and the dough ball gap junction. It seems to be a hard problem. So since we failed doing that, what I did was I took a single line, put a Morse Lagarde on it, and then I put in the dough ball gap junction, and asked if I could do it with the Morse Lagarde equation. And with the Morse Lagarde equation, I can do it. I stimulate it on this side, and I can get a wave to go across. This is a nonlinear kind of wave. It does not have a constant velocity, but notice that it does die off as it penetrates the islet. So then I asked, what's the value of the effective diffusion coefficient that I needed for this? Well, I got a value of 1. Is that strong or is that weak? So if I want to ask this question, whether this is a strong value or a weak value, I compare it with the value that is required for synchronization, the value of sigma that is required for synchronization in this tissue. It turns out that I need, so this is the simulation for sigma equals into the 5 just to refresh your memories, this is sigma equals 1. And I get a partially propagating wave at sigma equals 1. At 10 to 5, I get a fully synchronized islet. It starts to get a little bit fuzzy at 10 to the 2, but I get a synchronization nonetheless. At sigma equals 10, again I start to see a wave that sort of gets reduced in amplitude but is passing across to the other side. At sigma equals 1, that wave is not passed, it gets spinning in the islet itself. So it would seem to me that you need 2 orders of magnitude, at least between 10 to the 2 and sigma equals 1, you have, in order to explain both synchrony and weak gap junctions within a single consistent model. Now notice that a synchronous model will not allow you to span sigma over this much magnitude, because it allows for a change of only about half in terms of effective diffusion coefficient. So we did some simulations, and we think that the Dober model is a much better way of going about it at parameterizations of the gap junction conductivity in these items. So I think I'm going to stop there, and I'm going to point out very briefly some of the other directions that we are headed in with respect to this work. So one of the very obvious things is we'd like to understand better the relationship of compartmental style models and homogenized models. There are interesting theoretical results that state that the behavior could be fundamentally different between lattice differential equations and full PDEs. So we'd like to explore that further. Of course, I pointed out to you earlier that I used some Morris Lagarde for this toy simulation, and I'd like to know the answer to what a Dover model does. It seems to be an interesting and challenging problem. We don't quite know where the difficulty lies, whether it's to do with the theoretical arguments or whether it has to do with the numerics of computing it, but that's an open problem that we're working on. So again, we're working on numerical schemes to improve performance in all of these models, which is a big deal for us. We've also worked on, I haven't said anything about actual insulin secretion, how granules are secreted in the presence of these oscillations. So there are separate models that we're working on with respect to insulin secretion, the traffic of vesicles from the Golgi body all the way down to exocytosis. And at some point, we'd like to build a more comprehensive multi-scale view of these things where we can embed a PD islet, a dual islet with dual oscillator models, and adding on the vesicle secretion models as well. In a related but separate work, we're also looking for metabolic markers in human diabetes studies. This is done with collaborators at the University of Pune and medical doctors at KEM Hospital. And we're looking to ask if we can use the metabolic profile of diabetic patients to understand better how they respond to diabetes treatments or what's different in their physiology per se. So we've not done any physiology in that direction, so if anyone of you is interested, I'm happy to help. And with that, I'll
So is synchronization relevant to resistance, and which is better, synchronization or desynchronization?
or desynchronization?
Yeah.
Okay, that question can be answered on several levels. So there are 2 questions. The question is, in that one question there are 2 questions. The question is whether the beta cells themselves are synchronized within an islet, and whether islets across whether several islets across the pancreas are synchronized themselves. And we don't fully know the answer to that. There are several. There's one piece of study that says that there could be an interpancreatic ganglion that could be synchronizing islets across the pancreas. Another similar theory is, for example, that the blood flow is in a certain direction, that all of the islets tend to see glucose almost at the same time, so they tend to be synchronized. And if they have the right frequency, then they will stay synchronized on these time scales. A third theory is that these synchronizations are mediated through liver and the glucose oscillations. These are the key components that synchronize islets. So that's intra-islet synchronization. Within the islet is actually fenestrated with blood vessels, so the islet probably sees glucose all at the same time. So it's not essential that gap junctions are synchronizing beta cells within the islet, but then if they're not doing the job of synchronizing, what are they there for? So the jury's out on all of these questions.
So again, drawing analogy with the cardiac system, can you think of something like an ECG for the pancreas, where it shows classified events?
Well, in principle, it's possible, but the field does not like to be invasive with respect to.
Just to get data like for animal models, and then.
I don't immediately recall anyone doing an ECG on pancreas, but in principle, it's possible. So if it gets really important, then one might develop biosensors for doing that. That would be a novel approach.
I mean, it seemed like you were putting a lot of effort into validating the numerics of your model, comparing it to compartments, that kind of thing. Do you have a similar effort with collaborators or your own work to tighten the experimental basis?
Yes. So we work very closely with Les Sattin's lab at the University of Michigan. All of this work is indirectly or directly influenced by his actual work.
So are you able to suggest experiments?
Yes, we are. There's many of them that we've suggested, and some of them we have been carried out. Yeah.
So in your oscillation model, is there any role for feedback from insulin signaling itself onto the islet cells? And is there any dynamic shuttling of the glucose transporters? So muscle and other tissues like GLUT4 gets upregulated. Does that happen in that?
Yes, that's a great question. Because it doesn't need to be in this model. So the model itself is independent both of insulin feedback as well as changes in the glucose transporter densities. That would have to involve a systemic model, and we have a little bit of work in that direction, but we are not quite sure, so we haven't put it out there. But I think it will be important. Not so much the insulin feedback onto itself, but maybe insulin feeding onto glucagon, and what is glucagon doing at the same time as insulin is. That story is not yet developed.
So, this is a question regarding this classification of different spikings and interesting patterns that you showed. Since you made a solution to this connection with other examples you showed, when you go into further, decline tissue bursting seems to be much more effective at removing calcium or.
Sorry, what was that last bit?
Referring tissue, for example, bursting patterns seem to be much more effective at recruiting calcium for causing the contractions rather than simple spiking. Is it more deliberate in pancreas as certain patterns are much more effective for
Okay. That's a deep and difficult question that I've been struggling with for several years. We don't understand what these different patterns are doing. It seems that the canonical pattern is the slow bursting, but then there are the fast bursting will reproduce an insulin dose response curve almost as well. So I'm not in a position to state exactly what these different patterns are there for.
Last question.
Now, once shown, is there a number of how many gap junctions are there? And does it matter? So stretch should matter, right?
Yeah. The number is not completely clear, but it will matter. Whether having gap junctions at all matters, whether it matters to the insulin secretion, whether gap junctions are strong or weak, I don't think that is an important question. But I think the business of trying to figure out how strong gap junctions are is independent in its own sense. It's an academic exercise, it's not important.
Other thing is that you brought in this integration neural models, of bifurcation and so on. But now there are these other ideas about how you could get bursting, not explained in terms of bifurcations and so on, but in terms of multiple scales of adaptation of spectrum. And I wonder if those models, they could provide additional.
So whose work are you referring to?
This is Kobayashi's model. So he.
I'm not familiar with this.
Maybe we can talk about it. So he basically introduces several time scales for adaptation.
Adaptation of. I mean, there are several time scales in the problem just by the nature of it being bursting at these different time scales. But I'd have to talk more about the adaptation.
Okay, let's thank the speaker again.